Let's get started by explaining what an analog computer is and how analog computers differ from digital computers. So what is an analog computer? Well, its name says what it is. Analog comes from the word analogous, which means something that is like something else or something that represents something else. And analog computers, whether they're mechanical or electrical or whatever, are devices that have some property that is like something else. A good example is perhaps one of the earliest analog computers, which is thousands of years old, called the astrolabe. So here's an astrolabe, which is a circular slide rule that has markings and pointers on it that you can move these rings and move these pointers and make predictions about astronomical objects. A newer type of analog computer is a carburetor. This is something you may have dealt with yourself. A carburetor has to deliver the right fuel-air mixture to a gasoline engine under varying conditions, under different throttle settings, under different amounts of airflow, and sometimes even a different temperature when it comes to choking the system so it has a richer mixture when the engine is cold. And so there are different devices in there, such as ports to meter the amount of fuel that goes through, venturis that create a vacuum so that under different amounts of airflow you get different vacuums to pull in different amounts of fuel. For the choke system, there are levers and cams and followers that can be adjusted so that you can get just the right amount of extra fuel when the engine is cold, and plus a heater system that pulls that choke off as the engine warms up. Most people probably don't think of that as a computer, but that's exactly what it is, an analog computer. We don't see carburetors anymore because modern engines have electronically controlled fuel injection. But perhaps the apex of analog computers were the fire-controlled computers used in World War II naval ships. And these were in everything from battleships to destroyers, and they used a number of inputs to direct the guns at their targets. So we had inputs from rangefinders and speed indicators, and also other inputs that had to be put in manually. So there was an army of technicians that operated these computers. And the information would come in, and out would come the azimuth and the altitude that you would point the gun, and these would all change depending on the firing ship's course and speed and the wind and the course and speed of the target. And if it was on land, the elevation above the horizon, or these computers were so fast that they could even fire accurately at moving aircraft. So they had to be able to point at the aircraft and properly lead it. And so if the airplane is this high, they had to aim higher than that so that the shell would arc over at the airplane and they'd have to lead it a certain amount. So they could put in all this information and get instant firing solutions to fire at their targets. They used a number of different things to do the calculations, such as differentials, which could do a subtraction operation. And they had cams and followers of all sorts of different shapes, spiral-shaped cams and other weird-shaped cams, which were rotating discs with either notches inside them or the edge was the proper shape and the follower would follow that edge, and you turn that cam one way and the follower would be pushed out or in and give you a solution based on the rotation. That would be a mathematical operation based on the shape of that cam. And the most interesting one would be the barrel cam, which sort of looks like a shortened and distorted baseball bat. And this was a three-dimensional cam where this could be rotated to one position, and then the follower could be in different places. So depending on the angle of rotation and where the follower was, you would get a different solution. I believe these were used for firing at aircraft to get the different lead angles for the aircraft at different altitudes and speeds. And so this was the epitome of analog computers. And these kinds of analog computers have gone back thousands of years. Now, more modernly, we also have electric analog computers. And let's take a look at how one of those might work. Let's say we have a system that needs an electric input based on temperature. So somewhere we have a temperature sensor. Let's say it's perhaps a thermistor, could be a thermocouple or whatever, and that goes into a system that will perhaps linearize it. What I mean by that is that the voltage that comes off of our sensor may not double as the temperature doubles. So if the temperature doubles, the voltage may go up by a factor of 4 or may go up by a factor of something less. And so we have some very simple circuitry that would linearize that so that if the temperature doubles, the voltage output would double. And let's take a look at the output of that. We have a single wire, so we're starting off with a simple temperature sensor and some pretty simple circuitry that would linearize the output of that. That could be done with a diode or a transistor because they are nonlinear. You put one nonlinear thing working against something else that's nonlinear, you can end up with something that's linear. And so let's say we have out here that 0 volts represents 0 degrees. Easy enough. Let's say it goes to 1 volt, and that would equal 1 degree. And 2 volts equals 2 degrees. And so we see we can have this information on this one wire, and let's say we need to handle more. Well, how about 3 volts is equal to 3 degrees? 4 volts equals 4 degrees. And we can keep going on like that, but let's say this needs to be able to sense temperatures from 0 degrees to 100 degrees. Do we want to go all the way to 100 volts? Well, we don't have to. We can condition the signal just by redesigning this box a little bit so that perhaps, well, same thing to start out with, 0 volts equals 0 degrees, but now let's make 1 volt equal 10 degrees, and 2 volts equals 20 degrees. So now we have 10 volts equaling 100 degrees. So we squeezed that whole range into a smaller range of numbers by simply conditioning the output to fit that range. And what's more, we can have fine gradations. So for example, how about, squeeze in here 0.5 volts. Well, that would now be 5 degrees. Or 2.5 volts would equal 25 degrees. So we can have gradations in between and an infinite number of them. 0.01 volts would be 1.1 degree or something like that if I'm doing the math in my head right. So we can have an infinite number of small gradations having basically an infinite number of steps inside here for our information on only a single wire. And once we get that, well, what can we do with it? We can go into an electric analog computer where we have circuits that can manipulate that. And we have circuits that can do, well, I'm going to show a symbol for something called an operational amplifier. These can be made with as little as 2 transistors. They used to make them with vacuum tubes. And there's 2 inputs and 1 output. I'm not going to explain this in detail because I have a whole series of videos on operational amplifiers. I have linked in the description below. But we can configure these operational amplifiers as perhaps a circuit that does addition. I'm not going to explain this, but I'll just show what the circuit looks like. There's a circuit that can do addition. Make a slight modification to it. And we have a circuit that can do subtraction or differences. Another modification. And we have a circuit that can multiply. And of course, here's our output here. So depending on the ratio of these 2 resistors, we have different multiplication factors. If we make this a variable resistor, we can multiply by different numbers. And we change the ratio of these resistors right, we can do division with the same circuit. We can multiply or divide. In fact, division can be done with simply 2 resistors. There's a dividing circuit right there, and the ratio of those resistors is the ratio of division. And so there's 4 circuits that can do add, subtract, multiply, divide that are 4 very simple circuits. And we can send this output into a computer and we can wire things together to multiply things, divide things, add things together, and get some other inputs into there and get a certain output or multiple outputs to do some particular job. Like I said, the circuitry is pretty simple. This would be maybe 1 transistor and a few support resistors or capacitors and whatever is needed to make that work. Each operational amplifier is like 2 transistors, although the modern operational amplifiers are integrated circuits and have more circuitry, but they're very simple. And so we can add, subtract, and multiply and divide, and we can even make circuits that will do square roots. And once you can add, subtract, multiply, divide, and do square roots, you can do any mathematical operation you can think of. And so we can build an analog computer that can take this temperature input and other inputs, put them together and get some desired output. For example, the fire control computers could use temperature sensors to help them actually aim the shot. And as a matter of fact, there was another analog computer that's very famous, the Norden Bombsight, that did use temperature sensors. I'm not familiar with the actual construction, but it was an analog computer that did have a temperature sensor. Although I don't know if it was electric, I think it was pretty much all mechanical. And the British had a bomb sight called the SABS, if I remember correctly, which was very similar to the Norden bomb sight. Another analog computer that had all these inputs and then an output. But once again, back to the electrical, we can do with this what we need. We just have to design things to go together to get the result that we want. Now let's see what happens if we have a digital computer. Now, by definition, analog, it's an O there. When we say analog in electronics, we're talking about something that is continuously variable, usually a voltage, which means I have a range of voltages. Let's just make up some numbers, minus 10 volts to plus 20 volts. And I can have any voltage in between. You name it, I can have minus 9.734 volts or plus 2.675 volts. You name a number, I can have it. And that's called continuously variable. So I have a range of voltages, and I have that on perhaps a single wire. When it comes to digital, we're talking about two voltages. So for a digital computer, now theoretically we could have more than one voltage. As a matter of fact, solid-state drives, SD cards, and USB sticks often use multiple levels of voltage to store information, but they're more the exception than the rule, and they're a special case, and there's problems with that anyway. But in digital, we're going to have two possible voltages. Typically, it's going to be plus 5 volts and 0 volts, or something nearby, maybe plus 2 volts or something, especially in modern systems. And plus 12 volts and minus 12 volts is another common set of voltages, but there's either these two voltages or those two voltages or two other voltages. We can't have anything else. So no continuously variable anything, plus 5 or 0, plus 12 or minus 12. And for working with these, since we don't know that if it's going to be 5 or 0 or 12 or minus 12 or whatever, we'll usually assign the number 1 to one of those and a 0 to another. And I'll be kind of interchanging that terminology as I explain what I'm explaining now. So let's say we have that temperature sensor again, and we go into a box. So there's our little thermocouple or whatever it is, incomplete circuit out here. But we want to have a digital output here. So let's say we have one wire. How many temperature levels can I handle with one wire? Well, I can have two voltages on there, either 5 or 0 or plus 12 or minus 12, but nothing, just one of the two possible voltages. So let's say I have one voltage, and I'll say that one voltage is going to be 0 degrees, and I'll make the other voltage 1 degree. So if we use the 0 and 1 type of thing, let's say that, okay, if it's a 0, it equals 0 degrees, and if it's a 1, it equals 1 degree. So if 0 is 0 volts and 1 is plus 5 volts, well, 0 volts equals 0 degrees, and plus 5 volts equals 1 degree. What do I do if I need 2 degrees? Can't do it. I can only have two possibilities with one wire. So I'm going to have some circuitry that's going to give me another wire if I want the number 2. So let's draw this over here and take a look at what we're doing. So I started out with 1 voltage was equal to 0 degrees, and the other voltage is equal to 1 degree. Now I have two wires, so what I can do is have 4 possibilities now, if I do this right. So now I can have 0 or 1. So if the first wire is a 0, I've got 0 degrees. If it's a 1, I have 1 degree. But this wire was 0 both times. Now I make this wire a 1, plus 5 volts or plus 12, whatever voltage that is. Now I can do that all over again. So if this is a 1, I can have that 0 again, and that'll be 2 degrees. If I make that 1 again, it's equal to 3 degrees. Okay, so I have 4 different temperatures I can put out on the digital wires. What if I want 4 degrees? Can't do it. I can only have 0, 1, 2, or 3. I can only have 4 possible states. So I need yet another wire. And so let's make that wire a 0 here. That gives me those 4 states. Now let's make that wire a 1. Now I can have 0, 0 again. That can equal 4 degrees. 0, 1 equals 5 degrees. 1, 0, that equals 6 degrees. And 1, 1 equals 7 degrees. So now I have 3 wires and I can have 8 possibilities, 0 through 7. What if I need the number 8? Got to add another wire, don't I? Okay, 0, 0, 0, 0, 0, 0, 0, 0. Then I go through it all again to go all the way up to, now I can get as high as 1, 1, 1, 1. So all 5 volts or all plus 12 volts, whichever that is. And that can finally equal the number 15 degrees. So with 4 wires, I can have 16 states, and I can, in this particular scheme, have 0 degrees through 15 degrees. What if I need 16? Here we go again. So now with a 5th wire, I can get up to 31 degrees. 0 through 31, 32 states. With another wire, I can have up to 63. It'll take yet another wire. 1, 2, 3, 4, 5, 6, 7. That's the right number. 7 wires to get up to 100 degrees. So we had that single wire, and we were able to go from 0 degrees to 100 degrees on that one wire, and we could have any fine division we wanted in between there. So we could have an infinite number of steps. Well, here, not only is it taking me 7 wires just to get up to 100, actually get me to 127 of the 128 steps, but to get to that 100, I need 7 wires. And I don't have any steps in between. I cannot go to 1.5. Not allowed. I can go 0 to 1, 1 to 2. If I want these fine steps, I'm going to have to add more wires, more steps, do some realigning here, saying, okay, how about 0, 0, 0, 0 is 0 degrees, 0, 0, 0, 1 is half a degree, 0, 0, 1, 0 is equal to 1 degree. I'd have to realign that and add more and more and more wires. And just because I have this number memorized in my head, if I have 16 of those wires, so there's 8, 16 of them, how many states can I possibly have? Finally, with 16 wires, I can have 65,536 possibilities, which means I can have the numbers 0 through 65,535 with 16 wires. If I need a bigger number, I need another wire. 16 wires is probably about enough to do anything useful. For example, when we digitize music, we use 16 possibilities because we can't really hear any difference between the different 65,536 steps when we have 16 wires. But here, to get all those steps, it's taking 16 wires, where I can still do better with 1 wire with an analog system. So what is the advantage of a digital system? Well, I'll get to that in a moment. I want to talk a little bit about how a digital computer works, and we'll compare that to an analog computer, and then we'll take a look at the advantages and disadvantages. So a digital computer, I'm going to make a little drawing here of a programmer's model of a 6502 processor. Why? Because I've actually programmed that processor. And what this has in there is 10,000 or so transistors. Well, that's a lot. Well, we couldn't even think of doing these kinds of things without integrated circuits. Remember, the first computers using vacuum tubes had as much as 20,000 vacuum tubes in a huge room, and all of the problems that go along with vacuum tubes, from heat to failures and whatever. Nowadays we can put, well, the 6502 had 10,000 or so transistors. Now we're putting trillions of transistors on a single chip, and we can do it fairly cheaply because it's all done photographically. So it's basically almost as simple as taking a picture and making copies of that picture. It's a complex photographic process. Otherwise, we couldn't think of doing digital computers. But let's look at how they work, and then we'll compare them to the analog computers and see why digital computers are superior to analog computers wherever they are superior to analog computers. So the 6502 is coupled with a memory bank, and I'll fill that up because we can these days cheaply. When I was working with these, memory was so expensive, even though this memory bank had 65,536 times 8, whatever that number is, transistors and other components that make it store information. And it could store 1 bit, which would be either 1, 1 or 1, 0, 1 5 volt or 1 0 volt point. It could store that many of them, 65,536 times 8 storage spots. And we could only fill about a quarter of that in the early days because memory was so expensive. And let's say it's completely full with all the memory, including the read-only memory that starts up the computer, and the other memory we can put programs into and store data and whatever. And there's some wires, 16 of them to be exact. 16 wires called the address bus. I'll just put an A there. And then 8 wires called the data bus that went in somewhere else, and I'm going to oversimplify this a lot. And so this computer had 3 pieces of memory inside called registers. One was called A for the accumulator, and then the X and Y registers, very simple processor. And here's what it could do. It could go to memory and pull out 8 of those bits of memory, 8 of those ones and zeros, which we call a byte, and it could store it into a place called the instruction register, and there's some circuitry in there that would decode that, make these voltages go here and there, and then finally come out with a one wire with a voltage on it that said, go through this sequence of operations. And so these instructions say, do this, now do that, and now do the other thing. Let's take a look at the things it could do. It could go into memory, just randomly pick a piece of memory, how about that one right there, and put it in the accumulator, or put it in the X, or put it in the Y register. Or another instruction could say, well, take what's in the accumulator and put it back somewhere else in memory. So it could take something out of memory to one of the registers, or take something from one of the registers and put it back into memory. Okay. Now, it could also take the number in a register and add it to another number and then put the result somewhere else. So it could do addition. And it could take a number and do subtraction. And you could add over and over again and multiply, or you could subtract over and over again and divide. And you could put the number in here and move all the bits right or move all the bits left if there was a use for that. And now we've said that we can add, subtract, multiply, and divide, and if we do a number of instructions, we can actually do a square root. And once you can do addition, subtraction, multiplication, and division, and square roots, you can do any mathematical operation you need. And so this microprocessor, by following those instructions, this instruction, that instruction, so it's somewhere pulling in 8 bits of information, sticks it into an instruction register, decodes that through some circuitry, which makes a sequence of events happen, which either pulls something in, puts it out, or adds, or subtracts, or moves some bits, or whatever. And it can also do a compare to see if 2 things are the same, and then jump to a different instruction if they're the same, and not jump if it's another. And I've pretty much exhausted what microprocessors can do. They only do about 9 different things. Even modern microprocessors that say, well, we have so many instructions, are really just built upon those 8 or 9 instructions that a microprocessor could do way back in the 70s. But they can just do them a lot faster these days and work on a lot more bits at a time. And that's all the microprocessor can do. So, with that ability, here's the difference between an analog computer and a digital computer. The analog computer, I will draw over here, can take something in, do something with it, I don't know what, and come out with a result. And the analog computer has to be designed from the ground up to do that operation. And that's all it can do. The digital computer can do anything you can think of that has to do with manipulating numbers and putting voltages out on some wires. All the things that computers do, from word processors to video games to rendering CGI videos, is all done with those just few instructions, all done from instructions in memory. So we can make a digital computer do whatever we want. That's why we call them general purpose computers. It does what you instruct it to do. The analog computer does what it's built to do, and that's all it can do. So there's a big difference in one of the advantages versus disadvantages. So what's the advantage of a digital computer here? It can do whatever you want it to do. What's the advantage of an analog computer? Well, let's take another look at the difference. I read an article in the 1980s in Scientific American magazine that explained the difference between digital and analog computers, and I loved their illustration. So let's say in a digital computer we want to sort some numbers. So we have some numbers in memory, but they're unsorted. We want to move them around until they're in numerical order. Well, there's a number of different algorithms or programming sequences that can do this, and they have different names, but they all have one thing in common. You have to take one number out, move it somewhere else, take another number, move it somewhere else, move this out of the way, moving these around until you get it sorted. And it takes time, and you have to go through the numbers again and again to make that happen. Some algorithms are better than others. Let's take a look at a sorting algorithm for an analog computer. Take a pound of spaghetti, and now what we're going to do is we're going to cut that spaghetti to different lengths. 1 centimeter represents the number 1, 2 centimeters the number 2, 3 centimeters the number 3, and 4 centimeters number 4, etc. And have that laid out so we have all of our numbers laid out. So now we take those pieces of spaghetti and we put them in our hand, and now we take our handful of spaghetti and hit it on the table, and all those pieces of spaghetti will fall down to the bottom and they will be sorted in the order of length. And now we can open our hand and take out the shortest one and the next shortest one and the next shortest one and put them down all sorted. So the operation of doing the sort was absolutely instant. We put that down on the table and it was sorted. But look at the setup. We had to cut all those pieces of spaghetti, then we had to sort it, and then we had to take it all apart. In the case of a digital computer, we have all of that information in memory, and it's very quick to put it in memory, but it takes time to sort it. Move this here, move that there, move this here, move that there, move that, then back, up and down, move everything until you finally have it sorted, and then it's ready to just pull right out. So the difference there is the digital computer takes a long time to do the operation, but the setup takes very little time. The analog computer takes a very short time to do the operation, but the setup takes a long time. And in this case, the analog computer was at a disadvantage because the setup of cutting those pieces of spaghetti is rather tedious. And then, of course, laying them back out is also tedious. And so the sorting was very quick, but the setup and takedown was time consuming. So there's an advantage of a digital computer over an analog computer. The digital computer can do whatever we want, but the analog computers tend to be very fast. Other disadvantage of the analog computer is an analog computer is designed to do one thing. Now, Derek showed a little square that he said was an analog computer. That was sort of programmable, but essentially by moving those wires around, you're rebuilding the circuit each time, and then it can only do that one thing. Where a digital computer, modern ones, can actually do multiple things at once. So, advantage of the analog computer there is fast. Advantage of the digital computer is it's versatile. Now let's take another look at an analog system versus a digital system. Let's look at that thermometer again. Here's our thermometer sensor. Goes into a conditioning box and out comes a voltage. So let's say we have a temperature of, how about 50 degrees, and out comes here, 5 volts. Easy peasy. But this is going through some circuitry, and we're going to have some differences in temperature. And when we build these, if we build multiple ones, the components are going to be a little different. So one box we put in 50 degrees and we get 5.01 volts. Another one we put in 50 degrees and we get 4.97 volts. So we don't get the same voltage out for the same input on two different devices that are essentially identical. As a matter of fact, as the temperature changes, and who knows what might change over time, these numbers might change. Problem we have here is integrity of the data. It might get changed from one side to the other. If the changes being small are no problem, then it's no problem. But let's say we have to go through another circuit and another circuit and another circuit, or especially when we have analog systems that make copies, like analog recordings. Every time we make a new recording, we introduce errors, and it gets worse and worse as we go down the line. So analog systems have trouble with integrity from one end to the other and repeatability. But when it comes to a digital system, assuming that the temperature of the thermistor will always be the same, since the output, I'll just show two wires here, between 0 volts and 5 volts is a pretty big difference. So it's very unlikely that some problem with integrity is going to change me all the way from 0 volts to 5 volts. And the circuitry that's picking this up will take, well, what if this goes over here and it's only 4.8 volts? It says, looks like 5 volts to me, and the output's going to be 5 volts, or it's going to treat it like 5 volts. So if the data's changed a little bit going from one place to another in a digital system, every time it goes through a stage, it gets cleaned up. If there's a slight change, 4.8 volts is close enough to 5 volts. It says still 5 volts. And if it comes in at 1 volt instead of 0 volts, it says, it looks like 0 volts to me. So the data is going to have high integrity because we introduce small errors. Those errors are cleaned up. So if I have those 8, 16, or how many wires, and I put in 010000001. Even though they might get changed slightly, when they come out the other side, it's going to be whatever I put in. So the data integrity is very, very high. Even though things can get changed, they get put back the way they were because they have to change a lot before they are corrupt enough that we can't tell the difference. And once again, if we make recordings, the recording is going to be the same, the same, the same. If the recording gets slightly degraded, well, it's going to be cleaned right back up the next time you do something with it. So this is one for digital computers. The data integrity and the repeatability are very precise. It's going to take a cosmic ray coming through and changing a transistor or something before a bit gets changed. And we do things to mitigate that anyway, such as parity or redundancy checks or whatever, to make sure that our data is intact, which you cannot do with an analog system. So, advantage of a digital system: we have data integrity. And then we have versatility. When we have a computer, we can program it to do virtually anything we want. Where when it comes to analog, we have simplicity and speed. So the analog system or analog computer's advantages are simplicity and speed compared to the high complexity of a digital system, although analog systems can be pretty complex. If you look at those fire control computers, you'll see what I mean. But still, as far as the number of components, I mean, to do that with a digital computer takes millions of transistors. Analog is simpler and faster. Digital has higher integrity and much, much more versatility. So that tells you the first things you need to know about what Derek was talking about. What's the difference between an analog system and a digital system? So his question was, are we building computers wrong? Is an analog system better than a digital system? Well, I think that's like saying a hammer is better than a saw. Analog systems have their place. We've been using them for thousands of years, and we are still using them, and I'm actually a fan of analog systems. My classes at RSD Academy are focusing on analog systems, although we do talk about digital systems and computers. I'm focusing on analog systems in part of it because that's kind of a lost art. I'd like to see more analog systems at maker fairs and such things as that. We just don't see enough analog stuff. Everyone does digital stuff because the digital systems are so versatile. I just get an Arduino and program it to do what I want. Let's do that with an analog system. That takes a little more of a challenge. So is analog better than digital? Well, once again, is a hammer better than a saw? They're two different tools that do two different jobs in two different ways, and I'd rather have a digital smartphone than try to make an analog smartphone because it simply wouldn't work. But when it comes to something that I need to be done very fast, such as calculate the fuel-air mixture going into a car and want to do it without a $1,000 computer, a carburetor, which is an analog system, would do that. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.